Dear colleagues, now we begin the second day of our conference and our morning session, and we start with Yuki Ishihara report on efficient localization at a prime ideal without producing unnecessary primary components.
Thank you very much. So I am Ishihara. I just shared my screen. Can you see it? Okay, so let me start. So first of all, I am very thankful that I have this opportunity to present my extended abstract. So efficient localization at a prime ideal without producing unnecessary primary components. So here is an overview of my slides. So first, I explain some backgrounds of my research. And second, explain double ideal quotient and localization. And third, I explain the main algorithm to complete localization at a prime ideal. And then we see some naive experiment about the algorithm. And finally, we see the summary and future work. So first, the introduction. So here is the setting. We mainly consider the polynomial ring over some computable field, like the rational field Q or finite field. And let this be the ideal generated by polynomials f1, ft. And we also consider the radical of I, like this. And the set of prime divisors as I, and the multiplicative cross set. Also, we see later the degree of potency of Q. And so here is a definition of localization. So for an AR of I and multiplicatively cross set S, then the localization of I with respect to S is like this. For example, for I, which is generated by x squared and x times y, the localization of I with respect to this S is just x. So the geometrical image of localization is like this. So this is a parity of this ideal I, and if we when we localize I by this maximal ideal, which is correspond to the origin, then the localization of I at the prime ideal P is just like this. So localization implies we extract some specific construction, specific structure of I. So in this example, we extract some curve, some this line and this curve from the original ideal. So and we recall some notion of ideal, like this ideal and prime ideal and prime ideal. And this is the examples of some notion of ideals. So we remark that the radical of a prime ideal is a prime ideal. So for an arbitrary ideal I, we can consider the primary decomposition of I, like this. So we can express I as the intersection of prime ideals Q1, QR. This is some generalization of factorization of polynomial. And we also consider some special, some irredundant parametric motion like this. And we also consider the prime dividers or associated prime ideals of I. It is the set of radicals of primary components. And we say the radical of Qi is a prime dividers of I. Then I remark that the localization of I with respect to S, some multiplicate B cross set S, can be computed through the prime decomposition of I. So like this. And the algorithm of prime decomposition can be have been studied very much. So we can compute the localization of I by using prime decomposition. However, the algorithm of localization using prime decomposition uses some unnecessary primary components. For example, so we do not need the primary component which does not appear in this equation. So such primary components are unnecessary. So my goal, my final goal is to compute localization directly without unnecessary primary components. So today, as a first step of the goal, I devised a method using minimal primary divisors without producing unnecessary primary components. So these are examples. So for an ideal generated by these polynomials, then a primary decomposition of I is like this, and the primary divisors of I is just x and xy. So and there are two types of primary divisors. Here, the one is isolated primary divisors, and the other is embedded primary divisors. So in this case, x is isolated primary divisor, and xy is embedded primary divisor. Since this is a geometrical image of the ideal and isolated primary divisors and embedded primary divisors, so x is equal to 0 is just this line, and the 0 point of xy is just this original point. So embedded primary component primary divisors is embedded in isolated one. So we also write the picture of primary divisors as a graph like this. So x is included in x square y as a set inclusion. So we can write a graph like this. So x is isolated and x square y is embedded. And another case, if I is either like this, then in this case, x square and y is isolated primary divisor, isolated primary components, and the others are embedded. So in general case, the graph of primary components are more complicated, like this. If I, so in this case, I has a primary decomposition like this. So Q1, blah, 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 Q2, 3, 4. And I has a graph of primary components like this. So Q1, these Q1, Q1, 2, blah, 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 Q1, 5 are isolated, and the others are embedded. So if we localize I at the primary ideal P34, which is the radical of Q34. So the localization of I by P34 is just yes, like this. So the localization of I is the intersection of primary components whose radicals are contained in P34. So in this case, this one, this one, this one, this one. So I would like to compute the localization of I. So here is the outline of my algorithm. So algorithm to compute localization at the prime ideal. So as I input, let I be ideal and P be a prime ideal. And as I output, this algorithm returns a minimal primary decomposition of I of the localization of I at P. So first, I compute the isolated primary divisors P1, PR of I. Then take then take each prime divisors contained in P or not. So if Pi is contained in P, then compute the Pi primary component Q and put it in the set of primary components. And otherwise, eliminate the unnecessary primary divisors like this. And repeat step 1, 2, 3 for new ideal until it satisfies this condition. So I explain the outline of my algorithm as this picture. So the final goal is to compute this localization. And first, it computes the minimal primary divisors, isolate primary divisors of I. Then check each primary divisors are contained in the radical of this one. So in this case, these primary divisors are not contained in this one. So just eliminate. Then these primary divisors are contained in this one. So then compute the prime components of respect to the each prime divisors. And the second, we compute the next minimal primary divisors expect the isolated one. So in this case, this one and this one, and check these primary divisors are contained in this one. In this case, this not and this yes. So eliminate this one, and compute the primary component is corresponds to this one. So Q23. Similar step. So compute primary components, primary divisors, and these are not contained in this one. They eliminate, and then finally we get the localization of with respect to the that of this one. So this is a outline of my algorithm. So in this algorithm, we do not compute the unnecessary primary components like these components, and yeah, just compute the necessary primary components here using computation of isolated primary divisors. So I will explain more details. And my algorithm uses double ideal quotient. So I explain it. So this is a ideal quotient, and I call this ideal double ideal quotient of I and J. So the double ideal quotient similar polynomial division, but there are some differences between them, like this. So in polynomial divisions, the f divided by g is always g, but in ideal quotient, it does not hold. For example, in this case. So when this equation holds, the answer. So the answer is here. So the equation of double ideal quotient holds if and only if P is a prime divisor of Y when P is a prime ideal. So by using this condition, the equivalent condition, we can check P is a primary divisor or not by using only just ideal Y and primary ideal P without computing primary decomposition of Y. So double ideal quotient is very useful to check primary divisors. So we also consider some modified type of double ideal quotient by replacing ideal quotient by saturation. Yeah. So we can consider 3 types of variant of ideal quotient like this. So today in my algorithm, the second one, so double saturation, is very important to compute isolated primary components. So before I explain that, I will note that some special localization of I, that is the equidimensional hull of I. So equidimensional hull of I is the intersection of primary components of I, which has some same dimension of I, like this. So for example, the equidimensional hull of I is just x. Since x has the same dimension of I, it is a one-dimensional in this case. And we can compute the equidimensional hull of I by using double ideal quotient was an analytic of extension x2. And the image of equidimensional hull is like a localization of I, like this. So yeah. So on the other hand, the double ideal quotient. So on the other hand, double saturation is a column localization. For example, if I is generated by this one and P, then the double saturation of I and P is this one So in the graph, the double ideal quotient, the double saturation is the intersection of these components, which is some column localization. So dimensional half is a low localization, and the double saturation is column localization. Then combine them, we can compute the particular isolated primary component of I, like this. So the equidimensional half of double saturation is in this case, so P is the isolated parameter divisor of I. Then we can compute the, sorry, wait, x square, yeah, sorry, this is x square, actually. So image of the combination of double saturation and the equidimensional half is like this. So combining localization and column localization, we can compute the particular isolated component like this. So also we can compute the impeded component like this by using equidimensional half. So, and then I explain my main algorithm like this. So first, I divide the parametric decomposition into some groups like this. So this is I simply say this is division is like this. So this is a parametric decomposition of I. Then in this case, I divide it in two classes. The first level, this is most minimal running components, and the second is the next level of components, and the third is the third level components. So we can divide the parametric component of class level of inclusion. Then we can compute you can compute the primary divisors of embedded ones by using a computation of isolated primary divisors like this. So like SI is like in this case the primary divisors of this parameter divisors can be computed by using these parameter divisors of prime components like this. So SI uses a computation of isolated primary components, isolated parameter divisors. So I mean, this means by using computation of isolated parameter divisors, we can also compute the embedded parameter divisors by using this ideal quotient. Also, we can compute the embedded parameter component from parameter divisors like this. For example, I use this ideal. Then the minimal parameter components of I is the intersection of this one, x squared and y. Then we compute the ideal quotient of I and this ideal. So here we get this intersection of component, intersection of ideals. Then we compute from this parameter divisors about parameter divisor P. We compute the parameter component of I by using equidimensional half. So then here is a detail of my algorithm. So first, check I is contained in P or not. And if P is a isolated parameter divisor of I, we can check this condition by using the double saturation. Then if P is an isolated parameter divisor, then we can just get the equidimensional half of double saturation is the isolated parameter component of I. And yeah, and here is a part of the computation primary components of I, which relates to the localization. So we can use double saturation and equidimensional half to compute particular primary components. Here, yes. And the ideal quotient to compute the embedded parameter divisors. So again, the image of steps of the algorithm, like to compute this localization. First, we compute the isolated parameter divisors of I, then eliminate unnecessary parameter divisors. Then, by using the necessary parameter divisors, we can compute the particular, we can compute parameter components related to them. Then next we can, next we compute the embedded parameter divisors. They eliminate unnecessary one. Then compute parameter components.
Sorry, Yuki, you have 30 seconds to finalize this talk. Sorry.
Sorry. So yeah, sorry. And yeah, here is the benchmark. So we can we see that some effectiveness of my algorithm and summary of algorithm. Yeah, so I devise some certain effectiveness my algorithm, and the future work I will explain in another example and the new algorithm without producing unnecessary parameter divisors. So that is so. Thank you for listening.
So please, please.
Sorry.
Have you implementation of your algorithm?
So I implement my algorithm on singular.
Thank you. It's nice. It's possible to get this implementation.
Thank you very much.
Thank you.
You.
If I let's continue our discussion. Please, your questions. Кнопочка.
My question is about lower bound complexity of the problem of localization. If all known lower bounds are the same that for the problem of primary decomposition, or not?
I don't know the complexity of this algorithm because so to consider the I use a global basic computation to this algorithm. So it is very difficult to consider the computation of complex of global computation. So yes.
Okay, but actually my question was
sorry. So your question is bound of complexity.
If you hope with new algorithm to get the algorithm with complexity which is lower than for the problem of primary decomposition, or not?
Sorry, so I cannot understand. So your question.
Yes, I also have a question. Is your code publicly available now?
Not yet.
Not yet. Hopefully in the future, right?
In the future.
Okay, thank you very much.
Sorry, thank you very much.
It's okay? Yeah. My question is about algorithm 1 and step 2.
Yes. Yes.
Yeah. Is it easy to check this?
Yes. So yeah, we have a granular basis of P. So by using a polynomial division, yes. So yeah, we can check this inclusion by using granular basis of P.
Yeah, I see what you mean. Thank you very much. Yeah. More questions, comments? No. So thank you very much again.
Thank you very much.
I see. Amir Hashemi.
I'm sorry. Yeah. I am scheduled to give the talk.
Werner Seiler. Yeah.
Should I share my screen?
Decompositions of monomial ideals and involutive basis. So please.
Yes.
Yeah.
Yes, I will share my screen. Let's see. Okay. Here it is. I hope you can see. Yeah, I see on the screen. Yeah, great. So let me first give thanks to the organizers of this conference to make this possible, that I can talk today about this work which is joint work with Amir Hashemi and Werner Seiler, as you also mentioned already. So Let us first look at some notations which we will use. We will denote the polynomial ring in n variables over the field K by the letter P. And by T, we denote the set of all terms in this polynomial ring, power products of the variables, which we denote shortly by multi-index notation. So there's a multi-index of exponents mu. For a subset of variables y, we denote by t indexed y the set of terms of a subring only on the variables y. And a cone will be a set of terms supported on a vertex term t and all its multiples with respect to a restricted term set ty, where y are the multiplicative variables. A cone decomposition of the subset of the set of all terms is a decomposition into a finite number of cones of this set S. So, and we want to look at decompositions for certain sets associated to monomial ideals. To such a monomial ideal, we can associate term sets S1, which are the terms in the ideal itself, and S2, the other terms. Involutive bases, we'll get to this in a moment, give cone decompositions of S1. In this talk and this work, we concentrate on cone decompositions of S2. We call this a complementary decomposition of the ideal. Such a complementary decomposition induces a K-linear decomposition of the factor ring, P over I. And this has been used already by Jani and Stanley for the computation of the Hilbert function. And by Ries, also for his Ries decompositions, he restricted the possible sets of multiplicative variables to such sets xi up to xn. There's a more or less folklore algorithm for the task of finding a complementary decomposition. I will not go through the algorithm in detail, but the input is a generating set of a monomial ideal. And then you pick one certain variable. Here we pick x1. You can see this in line 2, which is highlighted. And you look at all degrees in this one term which appear in the generating set, split, sort this in ascending order, and yeah, then more or less derive from this subdivision term sets in a ring with one variable less and apply the algorithm recursively to these derived sets. Since this algorithm is pretty well known in the literature, I will just mention that we, as a contribution in our work, have performed a complexity analysis of this. And here, two numbers are very important. The number m of terms in the generating set and the number lambda, where we look at degree differences in single variable degrees. They use this ascending order of the degrees which appear in this variable and all differences of adjacent members of this sequence, and build the maximum over all these differences. And the algorithm, arithmetic complexity of the algorithm is then given by lambda n to the n. Here lambda and m play an equivalent role. We would like to also present an alternative algorithm using involutive divisions. So let me first shortly recall what are involutive divisions. They are restricted division relations for monomials. Such a involutive division we denote by the letter L, and such division L assigns multiplicative variables to a term contained in a certain set of terms. And then involutive cones are introduced. Well, these are just cones as before, where x mu is the vertex and the multiplicative variables are the variables for the restricted term sets that we use as multipliers. And yeah, it's supposed to also satisfy the so-called filter axiom, which I'll not go into detail about. But the notion of involutive basis is important for our talk and our work. A finite set H contained in the monomial ideal is an involutive basis if each term in the ideal possesses an involutive divisor with respect to the division L. A very important example, but not the most important for our talk, is the Pomeray division. Yeah, you look at a term x mu, and you say that the class of this term is the minimal index k for which the variable xk divides this term, and then you assign the variables x1 up to xk to it. Most importantly, there is another division called the Jani division. We use this for our complementary decompositions. Given a set U of terms and a sequence of non-negative integers di up to dn, we denote a subset of U as the Jani class of U. This is related to this degree sequence, and it contains all terms which agree in their xj degrees with this degree sequence for all j between I and n. And we say then that a variable xi is multiplicative for a term u if the xi degree of u is maximal among all other terms having in the same Jani class starting from I plus 1. Good news is every monomial ideal has a Jani basis, so which is not true for the Pomeray division, but for the Jani division we can obtain always a Jani basis, an involutive basis. Now we associate also a certain data structure to a Jani basis or general set of terms, the Jani tree. Each node in the tree has a label TV, where T is a term that encodes a Jani class of the set, and V is the set of multiplicative variables that are multiplicative for each term in the set in this Jani class, which belongs to the node. Let's look at an example here. 3 terms in the set U. The root is indexed by the term 1. It's the Jani class with empty degree sequence, and it corresponds to the whole set. And then this is split up degree-wise. In the first level from the top, we split by the x3 degree, and then in the next level by x2 degrees, and then by x1 degrees. And note that we always list the child nodes from lowest to highest degree. This is here relevant only for x3 degrees. We have degree 1, 2, and 3. And so one can also easily read off which variables become multiplicative. Here, for instance, the variable x3 only gets multiplicative for the term having maximal x3 degree. Okay, this set is not yet a Jani basis. On the next slide, we have completed the set to a Jani basis, and denote written as its Jani tree. Here, 2 new terms had to be added. They both have x3 degree 2, so the second branch is split into 3 sub-branches. If we compare to the Jani tree before, the middle term here is still contained in the completed set, of course. But here in the original set, it has had the multiplicative variable x2. In the bigger set, this variable is no longer multiplicative, as you can see in the second branch from the left. Okay, so this is a Gianni basis, and from this we can describe the also already known algorithm for complementary decomposition. It uses a traversal of the tree, and for each node we look at the leftmost child, the minimal child node, and then in line 9 of this algorithm you can see that to the decomposition D is added a certain cone associated to, or a certain number of cones associated to this child node. So in this example, I've colored the nodes which do contribute cones to the decomposition in the color red. The white nodes are either the root or not the minimal children nodes of their respective parents. The yellow nodes are minimal child nodes, but due to certain degree reasons, they do not contribute cones. So this is why I colored them differently. Also for this algorithm, we've performed a complexity analysis. If we, again, our input set is a set of terms, of m terms. And this time another parameter is important, the parameter tau. It's the maximum of all single degrees in any variable in any term of this set. And then the arithmetic complexity of the algorithm, together with the computation of the Gianni basis, is given as shown here. M plays here only a minor role compared to the parameter tau. So you would expect this algorithm to be high complexity for sets where the degrees in some variables are very high. But the costly part of the algorithm is the computation of the Gianni basis. Once you have it, then you can assume that you have computed the Gianni tree on the run, and then you only have to perform a traversal of the tree. So the costly part is the computation of the basis. This can be improved by the Gianni-like division, which was proposed by Gert and Blinkhoff in 2005. It's no longer an involutive division in the strict sense, but it's a generalization of this concept in a certain sense. It's a technical construction. Let me say that, again, you have a finite set of terms, and you look at capital U, and you look at a term, small u, in this set, and then you look at the Gianni multiplicative variables and the non-multiplicative variables. For the Gianni division, only the multiplicative variables were enough, because you then also know which variables are non-multiplicative. But here for the Gianni-like division, the non-multiplicative variables get closer treatment. For each of these non-multiplicative variables, a non-multiplicative power is defined by a certain minimal degree difference. The exponent of this power is defined by such a degree difference. We collect all non-multiplicative powers of the term u in the set NMP, and the non-multipliers are then all terms which are divisible by any of these non-multiplicative powers. And the multipliers are then accordingly the other terms, those that are not divisible by any non-multiplicative power. And the notion of Gianni-like divisor and Gianni-like basis is then pretty straightforward. Okay. Also to the Gianni-like division, we assign a data structure, the Gianni-like tree. again, the nodes have the two informations we already know from the Jani tree. This does not change, but an additional information is written into each node. This M, this set M, is just this set of all non-multiplicative powers, which are common to all terms in the Jani class belonging to the node. So in this example, we get a Jani for, again, the same ideal as we already had in the earlier examples. We get a Jani-like basis having one element less compared to the Jani basis. But in each node, we have to write the non-multiplicative powers. So, but these non-multiplicative powers then allow to get the complementary decomposition also from this smaller Jani-like tree. The algorithm has a very similar structure to the one, to the Jani algorithm, so to speak, the last algorithm. But here in line 8, you can see that the assignment of cones is a bit more complicated. Well, you use the Jani-like non-multiplicative powers to assign these cones. And again, I have here denoted in red the nodes which contribute cones to the complementary decomposition, and white and yellow stand for the same as in the last example. Yeah, so we've lost, with respect to the example before, one red node, so to speak, but one of these 5 nodes here contains the necessary information to, yeah, in a sense, reconstruct all information that's contained in the Jani tree. So all of this in this example does not seem to be so relevant because only it's only 2 nodes left or something. But in general, especially when the degrees get high, as I mentioned already, the complexity of the Jani basis is high when maximal degrees are high, and in such cases, the Jani-like division and tree really is a marked improvement. Let's consider for n greater or equal to the ideal I, a simple ideal generated by x1 to the n up to xn to the n. The minimal Jani basis then has n to the n minus n elements, or yeah, exponentially many elements. Whereas the Jani-like tree and the Jani-like basis is just the minimal generating set. And the Jani-like tree has a number of nodes which grows polynomial with n, and what is more, even only one of the nodes here in this example encodes all necessary information for the complementary decomposition. So it's a huge improvement in examples such as this. Okay. In a certain sense, a second distinct part of our work is the following. Namely, Hironaka in 1977 also defined the construction for complementary decompositions of monomial ideals. He used these projection maps, which you can see at the top of the slide, where a term gets projected down to a subring by setting the first few variables to 1. So yeah, the first variables get projected to 1. And yeah, and then it's a very technical definition here in Hironaka's constructions. And his construction by which he is able to give a complementary decomposition of the ideal. However, not for every monomial ideal this decomposition is a finite one. So in general, Hironaka will get an infinite number of cones in his decomposition. Now, we in our work showed that his construction yields a finite decomposition if and only if the input monomial ideal possesses a finite Pomeray basis. And this is also called quasi-stability, the property to have a finite Pomeray basis. So Hironaka's construction gives, in a sense, another equivalent description of the property quasi-stability for monomial ideals. And our proof of the theorem is, in a certain sense, constructive in the way that we give an algorithm to compute the finite complementary decomposition in Hironaka's sense for a monomial ideal given by its minimal Pomeray basis. Again, I will not present the algorithm in detail, but yeah, the class of some terms plays, of course, a role, as it plays a role in most things which are connected with Pomeray basis. And also here in line 10, the second to last line, we see that we have to perform certain auto-reduction operations during the course of this algorithm, which can be a costly operation. The reason why we have yet not performed a complexity algorithm analysis of this algorithm is that we were able to prove that the Gianni algorithm actually produces the same output as the algorithm 4 presented just now for the Pomeray basis as input. Because actually the Pomeray basis and Gianni basis are the same in this special case, and we can assume that the Gianni tree is given alongside the Gianni basis. So then we have to simply perform a traversal of the Gianni tree and not have to perform this algorithm, which relies on the auto-reduction procedure. Yeah, and to finish the talk, let's look at relations of our construction or of complementary decompositions to other decompositions types. Namely, there are several ways to decompose the complement of a monomial ideal into simpler parts. The primary decomposition and irreducible decomposition are other ways, because, yeah, as we've seen also in the talk just now by my colleague, the primary decomposition is representing the ideal as an intersection of primary ideals. So the complement is represented as the union of the complements of these ideals. So yeah, this is in some way a coarser decomposition of the complement. And yeah, because the complementary decomposition for these monomial ideals contain, in a sense, more information, we can compute and reconstruct the primary and irreducible decompositions from the complementary decomposition. But this is not the best way to do this task, because faster specialized algorithms exist for this. It's not surprising as, well, if you have to compute slightly less information, then it's not surprising that some algorithms will be faster for these tasks. Yeah, the algorithms by Gao and Zhu, as well as by Rune, are here worth mentioning. Rune's algorithm is, as far as I know, the fastest algorithm for irreducible decompositions. So, by this I finish my talk, and I thank you for your attention. Thank you.
Yes. Is there any hope to extend these ideas and this approach to binomial ideals?
This is a very interesting question because I do know that for binomial ideals, there are very interesting constructions which are also, in a sense, combinatorial because you need the combinatorial structure for the monomial ideas, of course. But yeah, there are ideas such like I just mentioned this buzzword, strange monoids or some. I think a scientist called Karle has worked on this, and so there is, in a sense, a combinatorial structure for binomial ideals, and perhaps this is in some way possible, but I don't know actually. Yeah, it's a very interesting question, though.
I see. And also, given the monomial structure of your input data, could you please comment maybe on the relations to toric geometry?
Toric geometry. Yeah, well, toric geometry, of course, in a sense, you need the structure of binomial ideals, which is a bit more complicated and more involved. So, in toric geometry, of course, you define these binomial ideals by defining sub-algebras of some rings by relations between monomials. Yeah, the monomial ideals theory is just, I think, not powerful enough to describe everything in toric theory. But it is known that in toric theory there exist many examples where involutive bases are not the most optimal thing. So actually Vladimir Gerd proposed Zhany-like the Zhany-like division together with Yuri Blinkov to address this problem, to make the involutive structure more useful for toric ideals. Yeah.
Okay, yes. Thank you very much.
Okay.
Any further questions, comments?
So, thank you. More questions, comments? My question is about your complexity estimates. Mostly it's O capital of something, yeah? O capital. What about more exact estimates using, say, theta capital?
I must say that I am not the best expert on complexity. This is, but we can, I don't know, but we can use your question as perhaps input for further refinement of our results. It's
okay.
So yeah, perhaps not only, it's interesting. The worst case complexity, of course, is in some ways can be bad for the Zhany division, but the medium complexity, the expected complexity for most cases that will appear is in most of the times better. Yeah. Okay.
Okay.
Yeah. Thank you for your question again.
May I complete the comments by Matthias?
Yeah, okay.
Can I do it, Timur?
Amir is a bit more into the complexity, so I think it will be useful for Amir to make a comment here.
I don't know if I have the permission to talk or not.
Of course. Please go ahead.
Okay. Thank you. Indeed, the kind of complexity that we addressed here in this work is just the arithmetic complexity and not the bit complexity. I am not sure if your question returns to the bit complexity or not. Indeed, this complexity shows the a number of decompositions that we construct during this procedure. So I mean that the final decomposition may contain less than the number of components and decompositions that we construct during this procedure. So we can consider the bit complexity of this procedure, but I think it's perhaps not useful for the comparison of the procedures. But here just we wanted to show that what is the dominant factor in the construction of the decompositions. As you see here in this slide, tau plays the main role. So the degree, the difference of the maximum degree that we have in our minimal generating set in the construction of the Johnny basis is the dominant factor. But that is not the case for the classical algorithm, as there M and tau plays the equivalent role. If my answer does not concern your question, so please let me give more information.
Okay, yes, thank you very much for your comment. Well, I guess that is the answer to the question. Yes.
So shall I stop sharing my screen?
Yes, I guess so. Yes, thank you very much for your very nice presentation.
Thank you.
We have
It's okay now? Okay.
Раз, два, три. Okay, let's start our second morning's session. And the first talk is by Başak, Karakaş, and Zafeirakopoulos, using GAN to produce real-rooted polynomials of low degree. Let's start.
Thank you. Hello, I am Başak Karakaş from Gebze Technical University in Turkey, and I and my advisor Zafeirakopoulos have been working on creating real-rooted polynomials of low degree by using generator adversarial networks. Today's talk, I want to mention what we did until now and what we plan to do after that. In this presentation, firstly, I want to talk about mathematics and machine learning, and after that, I want to give an answer of the question why we want to do something on this area. And after that, I'm going to mention our problem, but firstly, talk about the framework of GAN and what is the idea under it. And after that, how we use a GAN network to creating real-rooted polynomials and how efficient it is, or etc. Firstly, when we look at machine learning for mathematics, there are a few and recent studies in this area for mathematics using machine learning, few and recent. And in addition, their success is not always very high, sometimes really high success they achieve. For example, in here we have 6 different examples. Önal and Zafeirakopoulos try to calculate the volume of a polytope, or try to compare volume of polytopes in their studies. And they use feed-forward networks, autoencoders, and end-to-end networks for doing this. And with this study, they intend to start a discussion about applying machine learning techniques to computationally hard geometric problems. In second, Lemaire and Charton try to integrate, try to make some symbolic integration and try to solve first and second order ordinary differential equations. They use sec-to-sec method when doing that, and they achieve a better performance than some commercial computer algebra systems such as Mathematica or MATLAB. Bernal and his colleagues focus on the real discriminant locus problem as a supervised classification problem, and they need key nearest neighbor and feed-forward neural networks to classify this. And Matthew England mentioned 2 problems about cylindrical algebraic decomposition. One is deciding when to precondition computer algebraic decomposition with Grosvenor basis, and the other is choosing a heuristic to select the variable ordering the cylindrical algebraic decomposition. Charton and his colleagues also train a neural network model to learn mathematical properties of differential systems. They show that by training transformers, advanced and complex computations can be learned. For example, local stability, behavior at infinity, and controllability can be learned by using this. And lastly, last example, Yanko He, ranging from geometry to representation theory or combinatorics to number theory for different fields, different areas. He focused on how efficient using machine learning techniques is. And he notes there is really good studies in these areas, really efficient studies in these areas. Okay, so we said that there are few and new studies in this area. So we want to contribute to the idea that machine learning can be used for solving mathematical problems. So we want to do that by carrying out a study in symbolic computational area, symbolic mathematics area. And then we decide our program as a generic real-rooted polynomials. Then let me talk about firstly what is GAN framework. Goodfellow and his colleagues in 2040 put forward as a new idea. This idea is, they said, two-player min-max game. This means this idea includes two different neural networks. One is generator, you see as G, and one is discriminator. Okay, and in this architecture, Z is a noisy data from any distribution. And G of Z, what G generates by receiving this data. And discriminator takes two different data. I explain it a little bit later. And gives an answer between 0 and 1. Let's first check the discriminator. Discriminator receives data from two different sets. One is real data, and one is fake data set. And it tries to decide a data it receives is a fake or real. If it gives an answer, for example, it gives a data x, and it says d of x is 1, that means d of x is real. It thinks it is real. Or d of x is 0, that means discriminator thinks x is fake data. So discriminator wants maximize this cost function. What is the cost function? When it receives a data from real data set, then it wants to maximize d of real data. On the other hand, if it takes the x for fake data set, it wants to minimize the fake data. That means it is, since it is between 0 and 1, it wants to maximize y minus d of fake data. So in general, for this cost function mean of this sum, d wants to maximize it. On the other hand, let me check generator. Generator take noisy data. For example, it takes this data from normal distribution or binomial distribution, what the problem says us. Then it tries to create a meaningful data. The meaningful means in here, create a data similar to real data. So how it understands it is similar or not? By taking the output of discriminator. For example, discriminator receives g of z, and it says d of g of z is 1. That means generator creates similar to real data. Or it is 0, that means not similar to real data. So G wants to maximize d of g of z because it wants to create similar data. So that means it wants to minimize 1 of d of g of z. So the cost function is mean of this, and the objective function is minimizing this cost function. When we combine them, the main aim in here, in this architecture, is that G wants to fool discriminator. How it achieves this? If D does not distinguish a data is whether it is fake or it is real, that means generator achieve to full discriminator. Okay, let's first check this value function and this objective function. We said that discriminator wants to maximize this function and generator wants to minimize this part of function, but this is not important for generator, so we can write like that. So what could follow says this is a two-player discriminator and generator min-max game. So, okay, then they give an algorithm for this structure. Let's check this algorithm. For all iteration, for m noise sample, and m real sample, first they update discriminator by try to maximizing this loss function, this cost function. And after that, for m noise sample, they try to minimize that, and by taking that, they update the generator, weight of the generators. And when it stops, we say that if generator achieve to full discriminator, it should be stop because we want this point. That means discriminator doesn't decide it is real or fake. That means whatever a discriminator receives as a data from real set or fake set, it gives an answer near to 0.5. Then we can check to stop iterations this knowledge. Okay. By using this idea, we try to create real-rooted polynomials. First, what is real-rooted polynomials? If a polynomial has only real roots, it is called real-rooted polynomials, and we can represent a polynomial like this. It is a degree D polynomial, and AI is coefficients of this polynomial, and it is real numbers. Okay, in our structure, we need to create real data set. So firstly, we try to start degree 2. For degree 2, we just choose two roots between the integers 1 to 32, and we just multiply x minus x1 and x minus x2. After that, we normalize the coefficients between -1 and 1, because generator gives us a solution -1 and 1. So we don't want to direct discriminator give a different kind of output in real data set, from real data set. Okay, then, how is our GAN? What is the structure of our GAN? How is our networks? Loss function, cost function, and optimization is what? And then I talk about the training part. This is the similar of what could follow and colleges suggest. But we have some differences. For here, we have mix and combine the data. For example, I explain why we did it. Okay, let's start first with discriminator. This is our network. This is a multi-layer perceptron with two hidden dense layers with 64 neurons for each. And in input layer, we have a vector with 3 elements. These are coefficients of a polynomial of degree 2. And in the output layer, we have just a number between -1 and 1. Actually, it is 1 and 0, 1 or 0. In hidden layers, we use LU with activation function. And in output layers, we use sigmoid to find 0 or 1 with threshold value 0.5. This means if the output is smaller than 0.5, that means this is not a real rooted polynomials, discriminator says us. If it is greater than or equal to 0.5, discriminator says it is a real rooted polynomials. And generator, it is a similar network, but it is also multilayer perceptron with 2 hidden layers with 64 neurons in each layer. And this is noisy data. We take noisy data from normal distribution. And after that, we get another vector. This is gz1, g of z1, g of z2, g of z3 is coefficients of our coefficients of polynomial. For example, g of z1 x squared plus g of z2 x plus g of z3 is a polynomial what G generates. And all layers, we use LU as an activation function. So we have numbers in here between -1 and 1. Okay, let me first explain why we combine and mix the data. We don't want to affect discriminator's decision by giving ordering polynomials. For example, if we give m times real polynomials first, and after that, if we give m times fake polynomial to discriminator, maybe it can change its decision, etc. We don't want to do that, so we combine and mix data. When we combine it, we also store the labels of this data. So we have a supervised classification problem in here. Because of this, we use binary cross-owned entropy for loss function. This is the same idea what could follow says us. For example, if our x data from real data set, that means yi equal to 1, that means this is 1 and this is 0. So this 0 and the loss function only includes this part. Or it is a fake data, that means yi means equals 0. So this part is 0 and this part is 1. So the cost function only includes this part. It is similar to what Goodfellow says. So our aim, and the discriminator aim in here, maximizing this cost function, the mean of loss functions. For generator, when we try to use minimizing d of g of z, it is not really good. It doesn't give really a good solution for us. So we try to find another loss function, and we say it is p loss with p, and we try to minimize the mean of these p losses. What is p? For degree 2, it is related to discriminant. We know that it is really trivial. It is really trivial. We know that, for example, V is a vector ABC, like we get from generator, and then this represents ax squared plus bx plus c. Then we our p function is b squared minus 4ac. That means if it is smaller than 0, that means this is non-real rooted. But it is greater than or equal to 0, this is real rooted polynomial. So we want to maximize this function. So we want to minimize minus of mean of this function. This is our objective function in here. Do I have 30 minutes?
You have 3 minutes.
Okay. I want to check.
Sorry, 10 minutes because you start after 10 minutes.
I will check. Thank you. Okay, thank you. Okay, in training part for degree 2, we use the training and test data set contains 1,000 and 200 polynomial respectively. And we use stochastic gradient descent with learning rate 0.0002. We use this because if we use 0.002, it does not work good. In this, and also we use the accuracy metric for discriminator. You can see in this graphic, when we have 200, when we give 200 polynomials to 200 noisy data, okay. When we create 200 polynomials with generator, in the beginning, we have too many non-related polynomials. It generates too many non-related polynomials. But after a few iterations, it generates nearly all related polynomials. And we show that when the accuracy reaches close to 0.5, by examining clusters containing 60,000 randomly generated polynomials, we verify that the efficiency of G is near 0.99. And until now, we did some work for degree 2, and after that, we try to find generalize this idea, because we remember we find a p-loss polynomial for degree 2, and it is really a simple polynomial. But for degree D, we don't use discriminant idea. For degree D, we talk what we do for this. Since we use we take gradient this function, we need a differentiable value function. So lots of idea, for example, finding number of related polynomials and increasing it, maximizing it, does not work in here, because the way of finding this not differentiable, not gives us differentiable value function. Then we talk with Mohan Ravichandran from Boğaziçi University, and this is the joint work with Mohan Ravichandran. We focus on a theorem. This theorem says us something to finding non-negative, finding related polynomials with non-negative coefficients. For example, in here we have a degree D polynomial, and all AIs is non-negative numbers. And theorem says us these two are equivalent. If and only if P is real rooted, the infinite top list matrix has only non-negative minors. Let me explain what is minors. By the way, this is top list matrix, infinite top list matrix. We can write the coefficients A0, A1, A2 to AD, and after that we write zeros, 0, A0, A1, A2, etc. like that. And this is infinite top list matrix. And what is the minors? A minor is a determinant of K by K matrix, which is intersection of K rows and K columns. In this example, in this top list matrix, for example, second, third, and fourth rows. In here, K is 3, and we have second, third, and fourth rows, and first, third, and fourth columns. And when we take the determinant of this pink matrix, it is a minor of this top list matrix. Okay, then we talk about this because discriminant is also polynomial, and it is we take derivative of this. So if we find sum of negative minors of a polynomial, and we know that we want if it has only non-negative minors, we find a real-rooted polynomials. Then we try to maximize this loss function. And to do this, we want to minimize to this loss function also. By the way, we know that since it is an infinite matrix, we don't find all minors. We don't calculate all minors. So we choose R minors, and we try to train with this R minors. Okay, thank you for listening. This is our references.
Thank you. Other questions?
So my first question is, one thing is the efficiency, the success rate of the generator, and as far as I understand, it's very high, it's around 99%. But another thing is accuracy, because the complex, I don't think that the complex parts can be exactly zero. There must be some small residues. So what is the magnitude of the complex parts of the roots?
Okay, sorry, let me.
So yeah, they when the generator generates the polynomials and the real-rooted ones, I don't think that the complex parts of the roots can be exactly zero. So what is the accuracy? What is the magnitude of the complex parts?
Okay. When we train this network, we just check okay, let me understand thoroughly. We give input to discriminator, and we take the output, and we use threshold with 0.5, and if it gives 0, we say it is not non-real-rooted polynomials, and 1 is real-rooted polynomials, and then we try to find accuracy by using this.
Yes, I understand, but that's a different kind of accuracy. And what I mean is when you look at the generated polynomials and you look at the roots, and what is the magnitude of the complex parts? Because you know, there must be some kind of threshold when you decide which one is real-rooted and which one isn't.
Okay. Sorry. Sorry, I can't answer it now because maybe. Okay. Okay.
So I think the question is, after you, independent of all the training, etc.,
yeah.
When you compute a real-rooted polynomial according to the system, how do you confirm that is indeed real-rooted? You compute the roots, right?
Yeah, we compute roots. We use okay. Until now, we use the language Julia, and we use the function compute. It's
okay, and how much does the complex part deviate from 0?
Sorry.
Like how accurate it is? Is it up to machine precision?
Let me show this. For example, in here, we take 10 random numbers from a normal distribution, and we check how many of this is real rooted or how many of this not.
Well, yeah,
so I think.
But I think that it is a subject for numerical experiment.
Yeah, but that's what they are doing.
After some numerical experiments with GAN.
Yeah.
Okay, I have a few more.
You will get the answer.
I have some more questions. So you have a multi-layer perceptron discriminator, and my question is it really necessary for the polynomials? Because you can calculate how much a polynomial deviates from being real-rooted, for example, like root mean square of the complex parts. So you can sort of calculate it directly, and maybe you don't need a neural network in the discriminator part. Is it possible to just use direct polynomial evaluation instead of a network?
I think for degree 2, especially for degree 2, it is possible, but we check discriminators to stop our training part. We check G pulls it or not.
Okay, and another question is how well does you approach scales? So you talked about degree 2, and what are your results for higher degrees?
We don't have any good results for higher degrees now, but we try to work on this theorem, the idea, and we hope we get some good results.
And maybe a few words about your motivation, because it's not a particularly difficult problem to generate real-rooted polynomials by conventional methods. You can just take a product of x minus first root, x minus second root, expand it, and you get a polynomial. So what is the motivation for using GANs? Is it just a sort of experiment?
Our motivation is, now when we look at GANs, we show 2 different networks, and they work together, and discriminator gives a feedback to generator.
Yes, I understand, but but why the GAN approach?
Actually, I'm not really good at answering, but I thought, or we thought, it should be give good and efficient and maybe faster answer to us.
No. Okay, that's all.
Some remark about it.
Okay.
Thank you. And okay. Next page. Next page. Okay. Yes.
Пам-пам-пам. Вот так, вот так.
Yeah, actually, my question is also related to his question. I think, have you ever tried to analyze the resultant of the polynomial? Like, it's actually the discriminant for the higher degree polynomials. As far as I know, if you already know the coefficients for a third degree polynomials, it's very easy to know that if they have a real roots or how many complex roots, something like that. So
we thought to use using resultant for showing for finding relative polynomials, but until now we didn't find any derivative value function by using this. So we didn't use in this network. Maybe we can work on it more.
Okay, thank you.
Thank you.
Sorry, we have no time for more questions, and I think that we can continue after during the lunch break and so on. And only the short remark: it is not usual for computer algebra to use neural network and training to solve computer algebra problems. And maybe you know other computer algebra problem which somebody solved using machine learning training and only briefly. Do you know other algorithm which can be solved by training?
Okay, for example, let me remember the name, sorry. Lemaire and Charlton find a good way by using sec-to-sec method.
Okay, I think that maybe this is for future discussion. And just now we should thank
Thank you.
Next talk is by Nikolay, Osipov, and Alexey Kytmanov, simplification of nested real radicals revisited. Presented by Alexey.
All right. Can everybody hear me? Okay. First, I would like to express a deep gratitude to the organizers of this conference, both from the committee and from Sirius Center. It's a pleasure to be here. And I would like to give a talk on the topic which you can see. This research was led by Professor Nikolay Osipov, who is here. And if I cannot answer some questions afterwards, I guess he will answer. And let's start. Okay, our main subject of study is the radicals. And here you can see some examples of such expressions. And our point of interest is so-called nested radicals, when we have, say, square root under in an expression which is also involves roots. And here are some classical examples of expressions where you can, when you are able to decrease the nesting depth. For instance, the first two expressions are quite easy to understand, and they can be obtained by the formula given under the examples. Also, more sophisticated examples were given by Ramanujan a while ago. if you proceed, we can also obtain some similar formulas when solving cubic and respectively fourth degree equations by Cardano formula or Ferrari method. For instance, the first example here can be obtained by Cardano formula, solving cubic equations with one real root. And by the way, our subject of study is radicals over a subset of reals. And it is quite interesting that some of them, the general computer algebra systems can, for some examples, they can successfully decrease the nesting depth. And for other examples, which are also quite classical, they cannot. For instance, Maple deals pretty well with the first example here. But if you look further, the expression A and B both can be derived from the same equation of the fourth degree using Ferrari's method. And in fact, A and B are the same. And if we plug them into the Maple and evaluate evaluate the difference, then Maple gives you the correct answer is 0, which is 0. Okay, cannot be seen here. It's so 0. But nevertheless, if you try to, if you start with B and try to arrive at A, then Maple fails to do this. However, Maple gives you some other form of B, which is in some sense it's more complicated visually, but in some sense it's better than the initial form. Okay, the two main approaches to solving the problem of denesting are an approach based on Galois theory, and this approach deals with complex numbers and over the field of complex numbers. And the second approach involves Grobner basis technique, and here we can stay in reals without going outside. Okay, this is the main plan of the talk, and let's start with some preliminary results first. Okay, first we start with the definition of the extension. So suppose we have the field L, and the extension of L is finite, and let's treat it as the vector space over L. When we treat it as a vector space, there is a notion of basis, and so let omega 1 and omega n be a basis of this vector space, and we call it L basis. And for a fixed polynomial, we introduce the polynomials by the formula in the bottom. And now for any fixed collection A1, AN, we consider a system of polynomial equations. And the first proposition is that for any collection A1, AN, the system 1 has only a finite set of solutions. We will need this result later on for the special case of f when f is x to the q's power. Okay, a brief sketch of how do we prove this result. The proof is based on the theorem of finiteness, which says that if G is a Grobner basis for a system S, then under some assumptions, S has a finite set of solutions in Cn. And this result guarantees that the system 1 can be solved over the field, the given field. So why do we need this? So we need to introduce some more definitions. A non-zero number theta is called an almost, first start with the definition of Q's power. So theta from the field F is a Q's power of an element from F, if there exists such element in the field. And theta is called an almost Q's power in F over the initial field L, if there is a number from this field, actually L minus 0, which is a multiplicative group of L, such that theta is a power, Q's power of A up to some constant coefficient. And the first proposition actually, when we apply F equals x to the Q, this allows us to determine whether theta is a Q's power of some element, almost Q's power. All right, so let's proceed. Two more definitions, actually. This is the equivalent forms, and the bottom form is a bit easier to understand. A number alpha is called a real radical of degree n over p if alpha to the n's power is in p, and alpha to the power k, which is less than n, is not in p. One more definition. The radicals alpha 1, alpha s over the field p of degrees n1 and s respectively are called multiplicatively independent if if this condition holds only for trivial case when the powers are zeros. Okay, let's see. Yes, let's. Okay, and this is another classical result by Mordell, which says that if alpha 1, alpha s are multiplicatively independent radicals over the field P of degrees n1 and s, then the degree of the extension of P by alpha 1, alpha s is exactly the product of degrees of these radicals. And moreover, these numbers in the bottom form P basis of the extension P alpha 1, alpha s. So as a corollary, we have that there are no non-trivial identities with simple radicals. Simple, by simple we mean nesting depth 1. Then this is what this is the main result, which deals with simple radicals. And now let's see what do we have for doubly nested radicals. So, definition, again, let P be a real field. Then the field obtained by adjoining all the real radicals over P is called a complete radical extension of P and is denoted by R of P. So if we say if P is a field of rational numbers, then R of Q will contain all the roots, all the possible roots, like square root of 2, 3, etc., and cubic roots. So all the possible radicals, simple radicals. So it's a pretty complicated field. And for an arbitrary system of multiplicatively independent radicals alpha 1, alpha s over P, again we consider the field P tilde, and so the extension and its basis with degree being a product of degrees of radicals. And again, there is a classical result by Blomer, which says that if eta is a radical, simple radical, basically, and beta is a radical of depth 2, of degree R, then if beta belongs to R of P, then there exists some J such that such that for some radical from the basis omega J, the quotient eta over omega J is an almost R's power in P tilde over the initial field P. So to understand this, let's consider some simpler cases. So let omega be a square radical, so say square root of 2. We consider radical beta, which is a doubly nested radical. And now we want to know whether beta is an almost square, is an almost second power, almost square in P tilde, which is a P. So what is P of omega? It contains all the numbers a plus b square root of 2. Where say A and B are rationals. So, and again, two equivalent formulations, and again, lemma 1 star is more clear for understanding. So, beta, it says that beta belongs to R of P. If beta belongs to R of P, then either the first or the second inclusion holds. Okay, some examples. According to the scheme described above, we can denest this expression in the top half of the page. So this expression can be denested as a doubly nested radical over Q of square root of 6. However, if we take something very similar in the form, then it doesn't always work. So for instance, for gamma, it is impossible to denest. this radical over this field q square root of 6. Nevertheless, using some different technique, we can show that nevertheless it can be denested. So here we have nesting depth 3, and it can be denested to the depth 2. All right, now let's go further. And so now I have to say that the general theory ends for the nesting depth 2. And when we consider a higher nesting depth, then we can hope that for some special cases, some families, this procedure will still work. So it will be possible to denest, to decrease nesting depth for some special cases. And the first example here states that it is possible to prove that this radical gamma cannot be simplified. And the proof is quite algorithmic, and it involves, it is not computationally hard. So the computational hardness of the problem is in fact, the bottleneck is computing Gröbner basis for the system. And in this case, it is not computationally hard. However, if you look at example 2, if we change it a little bit and put the cubic root to the second radical, then the computational, the problem is much more complicated. And cannot be solved using the scheme which was described. Another example of the equation, so if you consider equation x to the fourth minus 4x minus 6 equals 0, then using Ferrari method we can arrive at the second formula for the real roots of this equation, where here rho is a cubic root of 2. And again, using lemma 1 or 1 star, we can show that this radical gamma cannot be simplified over R of Q. So again, here we have we can prove, the proof is constructive, that it is impossible to decrease the nesting depth. Okay, and more examples. Again, let's consider the radical gamma. And we go further and increase the nesting depth so that we have now delta, which is the radical of the depth 4. Again, it is possible to show that delta cannot be simplified. Basically, again, here we use lemma 1 star. So we need to check these two numbers, whether the number in the bottom here is not a square of the element from the original field, and it is obvious. And the second number is this, and again, it is quite obvious to show that it is not in P, because here we luckily get the radical of, in numerator we get radical of nesting depth 2, and it actually doesn't matter here. So in denominator we have radical of depth 3, and we have shown that it cannot be simplified. So the numerator doesn't influence the further calculations, so that we can show that delta cannot be denested. And finally, okay, our final example today arises from the equation which looks quite simple. X to the fourth minus x minus 1 equals 0. And again, Ferrari's method gives you this nice formula for the real roots. And we haven't done this yet, but we have a hope that it is possible to show that, again, this radical cannot be denested. But this is quite computationally hard problem, and it is still under consideration. So these are the key results of the work, and thank you for your attention. Any questions?
Question?
Alexey, show please page number 1, first page.
This one.
Yes. But second formula, why right part is better than left?
Right hand side. Okay. This is. It is not better. This is. This formula is the source of examples, which is in the top line here. So using this formula, you can construct a family of such things. And here you can see, here you have radical of depth 2, and here is the depth 1. And you can construct just a family of such examples. Mm-hmm.
Okay. Other question?
Thank you very much. Did you try to use the mathematical functions for denesting these radicals, like the function expand with extension options or the root function?
Okay. I think probably we main computation didn't involve this function, but for instance, if you take cubic equation and apply root of something, probably this function involves Cardano's formula. Mm-hmm. And you can get, for instance, expression for real roots using this method as well. But you need to check that you in fact have real root.
I see. Yes, and also it looks a bit tempting to replace some of the numbers in your radicals by symbolic variables and use symbolic expansion techniques, like expand into a series, for example, or again use the function expand procedure with several options. This might help, I guess.
Okay, Nikolay Nikolaevich will correct me if I'm wrong, but I think this method will not work with symbolic coefficients, because when you consider some particular example, like here, the procedure which involves, for instance, proof that the radical cannot be denested, it sticks to the computing Gröbner basis. And this this involves computations with for a particular equation, particular polynomial, and the examples were let's see. Okay, here, for example, to prove that it is impossible to prove that this radical cannot be denested, the bottleneck is Gröbner basis computation, and because they have very big coefficients, and yeah, if you plug some symbolic coefficients here, then it just will be impossible to compute.
Okay, thank you. One more question.
As far as I understand from the statement of the problems, for each case you try to prove that the radical cannot be denested. So this raises a question. Which radicals are more common? Is there such a thing? Denestable or not denestable radicals?
Well, of course, denestable.
So
It's much more
common.
Yes, yes.
Yeah, okay.
But yeah, it's like irrational numbers and rational. You have both, both sets are infinite, but you have much more irrationals than rationals, in fact.
Okay, thank you. And the short remark that the common problem of to simplify the roots of polynomial actually is the problem of Galois theory, but it connects not only the expression consists of radicals, but more common.
So just a few words to add. If you can prove, if you can denest the radical, it means you are lucky. You got lucky, basically. Okay. And we consider such cases.
Next talk is online talk by François Lemaire and Adrien Poteaux, decoupling multivariate fractions. Are you here? I don't see the speakers. Actually, we have 15-minute shift, and I ask if it is possible to reduce the time for.
Hi, hello. So François Lemaire is here. He just takes he needs a short while to connect.
Yes, I'm connected. And,
okay.
I'm ready to share my screen.
We have no sound.
You have no sound.
François, maybe there is some problem with your microphone. Может быть, это на нашей стороне? Нет?
We can hear you here on the web, on Zoom.
Yes,
Yes.
Now yes.
Also.
Okay.
Is it fine? Is it okay?
But please speak
loudly,
closer to microphone. Okay.
Okay, so
okay, it's good.
It's good. Okay. Okay, so I will share my screen. Okay, so can you see my screen?
Yes.
Okay. So I'm very sorry. I made a mistake with the schedule. I was planning to make my talk at midday, but in French time. I'm very sorry for the troubles. I'm going to present you a joint work with Adrien Poteaux, and my name is François Lemaire. I'm working at the University of Lille with François Boulier. So I will present you some work that was presented as a preliminary version at the Maple conference last year. So the talk is quite easy. So I will first motivate the subject, make a small demo, and explain more precisely what we mean by the decoupling of a multivariate fraction. So I forgot to say that the talk is about computing nice representations of multivariate fractions. And I will finish with the ideas of the algorithm. Okay, so let's motivate the subject. So we want to compute, in general, nice forms of a fraction. And as you guess, it's difficult to give a precise notion of what is a nice or compact form of a fraction. So the talk will not define properly what that is, and it's a bit subjective, by the way. But on some cases, most people would agree that a form is better than another one. For example, if you consider this fraction on the left, which is a nested fraction because you have a fraction in the denominator, I guess you would say it looks better than the expanding form, which is this one. Also, in biology, it's quite common to obtain this kind of fraction, which is a sum of fractions with different denominators. And if you expand this sum of fractions, you get a rather big fraction with one denominator and one numerator. And you see that all the terms, they get mixed together. And for example, the Cx, which was quite simple, appears now in many different places because it's multiplied by the denominator. So for those two examples, I would say that I prefer the non-expanded form. And the goal of the talk is to recover those forms from the expanded form. So fractions are a bit tricky because they can have many different representations, and the two obvious representations are the expanded form, so the quotient of a numerator and a denominator, and another form is to use a tree, or more generally a DAG of operations. And this DAG, in fact, here corresponds to the first example, A plus B over C, and which starts here. It's A plus b divided by, etc. So this tree would be more suitable for representing nested fractions, such as this one. And that's what we will do, the following. So why do you want a compact form? Well, usually a compact form will be easier to read because it's shorter and easier to understand. It would take less memory, and we'll see that in some example, it will also yield a better interval evaluation. And I will also mention some facts about fractions. So it's rather a personal feeling, but my feeling is that the fractions are a bit underrated in the computer algebra algorithms, and many algorithms, in fact, deal with polynomials. And if your starting objects are fractions, usually convert them to polynomial, recover polynomials, and then you need to guess what the fractions are. So typically, if you compute Grosvenor bases or triangular sets, you obtain polynomials. So there is some work to do afterwards if you are really interested in your fractions. And also, it's not so obvious to decompose, for example, fractions using something which looks like a partial fraction decomposition. So this multivariate partial fraction decomposition exists. It was developed by Stuttmeyer 10 years ago. So you have an equivalent for multivariate fraction. And also you have another way to decompose a fraction as a sum of fractions using a method by Lemaire. In both approaches, in fact, you decompose a fraction as a sum of fractions. But those methods will not deal with the problem of nested fractions. So what I will present you is really different from the decompositions of Stuttmeyer and Lemaire. Okay, so we are ready for a small demo. So the demo is made with some magical term. In fact, I will present you a magical function, which is obviously not magical, on a few examples to explain you how the algorithm is working behind. So let's start with a single polynomial p, which is quite easy. So it has a nice form, but when you expand it, it becomes a bit more complicated. This polynomial is irreducible, and if you use enhance function, forgot to. Yes, and I will remove the output from the. Sorry. So enhance can recover the original form here. Okay, let's start with another polynomial, which is a bit more complicated. So same thing, if you expand it, you get a larger form, and then you can recover the original form up to some signs here, because there is no uniqueness in the compact form here. Okay, and let's see a third one. So this one is a bit more complicated, but still you can recover the original compact form. Okay, so those examples were polynomial, but it also works on fractions. So that was the example in the introduction. You can try to factor, nothing happens, and with the enhance function, you recover the original sum of fraction, and the other one, which looks a bit like a continuous fraction, it also works up to some signs here. You have minus ones. Okay. Let's see some fractions a bit more complicated with nested terms. So it also works. And you might notice that here it's exactly the original form. And a last one, which is a bit more complicated. So you have a fraction here with many nested terms, the sum of quotient of continuous fractions. And if you expand, in fact, the denominator of this fraction p, you would get more than 400 terms. And the denominator would factor, giving you those terms. So obviously, on an example like this, if you expand the numerator, you get a very large expression. And if you enhance it, it takes just a few seconds to recover the original form. Okay. So you might wonder how the algorithm works. In fact, you might have already guessed, and I will give the answer. The title of the talk is Decoupling Fractions. And in decoupling means split in half two things which are a bit independent. And here, the algorithm will recover a nice form by detecting that some variables only occurs in some terms. So for example, here, this term involves A1, 0, A3, and B1, but the other terms do not. So using some reasoning on the variables, the algorithm is able to split independent terms. And finally, to show you that the algorithm is not perfect, if you take this fraction, which is quite simple, if you expand it, you get this fraction. And if you try the enhanced algorithm, it does nothing because, in fact, the independent terms here involve the same variables. So here you have x and y, y and x. So the algorithm has no clue to split Q as a sum of terms that are more simple. Okay. So I don't see if there are some. Okay. I'm looking at the chat just in case someone writes something to me. So that was the demo. And I can show you now what the algorithm is computing. And this will be the most technical slide of the talk. So I need to explain the definition. So if I take a fraction f, which is a multivariate fraction in the variables of the set x, if I introduce a partition of the set x, so I split x into different independent sets of variables, then we say that the fraction f can be decoupled with respect to the partition if you can write the fraction f as an expression a of f1, fp, where a is some fraction, and more importantly, where the different fi here are themselves fractions in the set of variable xi. So we've done a decoupling in terms of variables. So I have a fraction f. I split the set of variables into smaller sets of variables using a partition. And then I have a fraction f1, which depends on the variable in x1, a fraction f2 depending on variables in x2, etc. And then using those fractions, which have independent variables, and using something which is a tree, in fact, I'll be able to recover the fraction f. So let's see on an example what this means. So this was the example at the beginning, the biology example. And in fact, this fraction f can be written as a sort of a tree, a mixed tree with a tree and where leaves are fractions themselves. And the fractions themselves, f1, f2, f3, f4, and f5, they involve different variables. But on this example, there is a trick, because the variable x is put in the field of coefficient. So we see the variable f as a fraction with indeterminate c, v1, k1, v2, k2. And if you do this, you are able to decouple the fraction f with that form, where the different f(i)s have different sets of variables. So in that case, the fraction is completely decoupled. You cannot refine the partition further because the partition here is composed of singletons. Okay. May I ask how many minutes I have left to the organizer?
Have some shift and you have not more than 10 minutes, but I think that 7 or 8 minutes you have.
Okay. Okay, so you have some properties, and the most important properties is that if you have a fraction, you can define properly a finest partition for decoupling the fraction. So it means that you can split the sets of variables, and if you are doing that in the finest possible way, you get a unique partition. What is not unique will be the representation for the fraction. And the interest of having a decoupled fraction is that you expect to have a more compact and nicer representation, and also probably a better interval evaluation. So here are some two examples that you could find in the paper, and this is I'm not showing too much, but this dynamical system in fact can be written in this way with nested fraction, and it's done automatically, and can be nice to have this alternate form, which is a bit more compact. And if you perform, on another example, interval evaluation, so I'm taking this example with many independent variables. If you perform the interval evaluation, you have a huge amelioration, I'm sorry, it's a large improvement, because if you use a decoupled form, you get this interval, and if you expand the fraction and perform the interval evaluation, you get this interval, which is much larger. But of course, this is an extreme case scenario. Okay, so I will finish with the ideas behind the algorithm. So the algorithm is quite simple. It works in the following way. so to decouple a fraction f, if the fraction f cannot be decoupled, then that's finished. Otherwise, you will find a partition with two terms, so a partition yz of x, and write the fraction f using a fraction depending on y only, a fraction depending on h only, and build an expression from those two fractions gh using a tree A. And then you call recursively the decouple function on g and h. So the main problem is to find the partition yz. And it's based, in fact, on a property, a central property, which is that if a fraction can be decoupled, then it has one of the four following forms. So it's either a sum of two fractions with independent variable, or it's either a constant plus a product of two fractions with different variables, and also these two last terms, a constant plus the inverse of a sum, etc. So you have four different cases, and you have to develop some strategy to recognize each of these cases. That's what the algorithm do. So the algorithm will try each case, and if it succeeds, it will call itself recursively. So the four cases are exclusive. The two cases C1 and C2 are sufficient if you want to deal with polynomials. The first case, C1, is in fact a simple graph traversal. And the three last cases are a bit more difficult because they involve constant C and D, which need to be computed. So I first show in the case C2 how you would compute the constant C. And in fact, you have a formula which is quite easy. If f can be written as a constant plus a function of x times a function of y, then the constant C, is unique and defined with f minus fx, fy over fxy, where the indices are partial derivatives. And this formula, you can obtain it by hand, but you could also obtain it using the differential algebra package by François Boulier. So if you can use differential algebra to find the formulas. So you have a formula for C, and that's a necessary condition, and then you can continue the algorithm. And the last point before I finished is that there is a trick with the case C4 which can take you outside the base field. And to show this, in fact, you can consider this very easy fraction, xy plus a over x plus y. And this fraction, in fact, can be decoupled if you allow the square root of a. And so this fraction p is in fact equal to this big fraction here with square root of a everywhere. And this is decoupled because x appears only once here and y appears once here. So if in p a is equal to 2, then you would need a square root of 2 to express the decoupling. And if it's minus 1, then you get a complex fraction. And you cannot expect this because c and the constant here, in fact, are unique up to a small transformation, but you cannot escape the square root. So you sometimes need to take radicals to decouple a fraction, which was quite surprising for us. Okay, so as a conclusion, the code requires many heuristics And we use many evaluation tricks to avoid too many differentiations, because the differentiations, they tend to enlarge the data. And but the complexity is still polynomial in the number of operations on the fractions. So it's polynomial in the number of operations, but the fractions themselves, they might grow during the computation because of the differentiation. But the algorithm is quite practical, and even on large fractions, it works pretty well. Okay, thank you for your attention. If you have some questions.
Thank you, François. Other questions from Sirius Hall? Okay, let's see.
All right. I'm quite curious, for instance, if you take a sum of two fractions, two nested fractions, and suppose you have all different parameters there. So A, B, C in the left fraction, and D, E, F in the second fraction. And in some sense, it's an optimal form, the most compact form of this fraction. But now suppose some of the parameters of the second fraction are the same as in the first fraction.
Yes.
Say you have the first fraction with ABC and the second fraction again with ABC. So the question is, now in some sense it's not the optimal form, because you have like A more than once.
Yes.
And other, do you have any ideas how to get and does there exist a more compact and nice form for this expression? Thank you.
Okay, so that's precisely the situation our algorithm does not handle. So you might try the Stuttmeyer or Lennartas techniques. And they might work. For example, if you look at the first, I did try this. I think it was working. Yes, if you take precisely this example, that in fact it's a kind of example you mentioned, our algorithm does nothing, but I believe that the Lennartas decomposition will recover the sum of terms. And I think the Stuttmeyer also will do it. And you can have a hint in Maple, for example. I'm not cheating, probably using Q. So P, Q. Yeah, so here it works directly with partial fraction decomposition. So the Lennartas and the Stuttmeyer decomposition might split in smaller terms, independent, smaller fractions, but they will not handle nested decomposition. So what would be possible is to use both approaches. You first use our algorithm. If it does not work, you apply a Lennartas decomposition, which makes some splitting. And then again, you apply on each separated term our approach to try to further obtain a nested fraction. And also, you can also reapply Lennartas decomposition and so on. So it might be possible using a mixed approach and recursive decomposition to get something that is more pleasant.
Okay, thank you, François. And maybe more questions. We have time only for one short question. Okay, if no, from internet. If not, we should thank François again for very interesting talk. talk is by Elizabeth Kalinina and Alexei Uteshev from St. Petersburg University, and the topic is on the real stability radius for some classes of matrices. Will be presented by Elizabeth.
Работает? Так, все, да? Пусть тут лежит, да? Good day. First of all, I'd like to thank organizers for the organization. It's a pleasure to stay here. I'll try to be brief. I'd like to present our joint work with my colleague Alexey Uteshev concerning the real stability radius for some classes of matrices. First, I'd like to formulate the problem. A real square matrix is called Routh-Gurwitz stable if all its eigenvalues lie inside the open left half plane of the complex plane. Here it is the region D of the complex plane. For a stable matrix, for some real perturbation here, some eigenvalues of the perturbed matrix can cross the imaginary axis. That is the loss of stability. Given matrix norm, the matrix of Y of minimal norm is called the destabilizing perturbation. With this notion, the notion of distance to instability or real stability radius is connected. Here you can see is formal definition, the formula 1. Here eta is the maximal real part of the eigenvalues of the matrix. It is called the spectral abscissa of this matrix. We consider the case of Frobenius norm. This choice is not accidental. The Frobenius norm is more convenient. It is more applicable in control theory, but consideration of this case is far more complex than consideration of the case of spectral Poteaux norm. There are many works devoted to the case of spectral norm, but there are just a few works considering the case of Frobenius norm. In all works, the orders of the matrices never exceeded 4. There are some numerical methods for solving our problem of finding real stability radius in Frobenius norm, but all numerical methods have one problem. It is impossible to guarantee their convergence to the global minimum of the distance function. We try to combine symbolic and numerical methods in our approach to the problem. We are trying to find the univariate algebraic equation, one of whose zeros is equal to the square of the distance to instability. This distance equation is to be constructed analytically in terms of the entries of the matrix. This work is the continuation or an extension to our previous investigation. We told about that investigation last year in the conference CASC 2. Now we have succeeded with solving this problem for two classes of matrices in general, for symmetric matrices and for orthogonal matrices. Now I'd like to tell about methods that we need to solve the problem. We consider an arbitrary real matrix and its characteristic polynomial. We find the real and imaginary parts of F. Here you can see two polynomials, phi and psi. And we compute the resultant of polynomials, as you can see in the bottom of the slide. It is known result, this theorem. It says that the domain of stability, that is the set of stable matrices, have the boundary that consists of two algebraic manifolds. One of them defines the set of singular matrices, and the other defines the set of matrices having a pair of eigenvalues of opposite signs. So we need to find the smallest of the distances to these two algebraic manifolds. The distance to the set of singular matrices is known. It equals the minimal singular value of the matrix. And in this case, we can find the destabilizing perturbation too. In this case, it has rank 1. The distance to the second manifold is found in more complicated way. That is the problem for today. In our consideration, we started with this theorem that belongs to one law. In this case, the destabilizing perturbation is found, as you can see, and its rank is 2. As you can see, the function that we have to minimize is complicated. And the problem is to find the minimum of this function. We have obtained this theorem that connects the structure of matrix, of given matrix, the perturbed matrix B that we have to find, and the destabilizing perturbation in certain orthonormal basis. Here is the example. There is the matrix A, given matrix. Here is the matrix, transfer matrix to the new orthonormal basis. Here is the destabilizing perturbation. And you can see that the matrices, perturbed matrix and the destabilizing perturbation in new bases have certain structure. Now we consider the case of symmetric matrix. You can see the theorem that we have proved. This theorem gives the distance to the manifold of matrices with a pair of eigenvalues of opposite signs. It expresses this distance via eigenvalues of a given matrix. And here is one example. This is the symmetric matrix, its eigenvalues, matrix P of new orthonormal basis. This is the distance equation, and here is the distance to the manifold of matrices with a pair of eigenvalues of opposite signs. And here is the destabilizing perturbation. This is the case of symmetric matrices. And this is the second case that we considered, the case of orthogonal matrices, and the theorem that helped to express the distance to the manifold of matrices with two eigenvalues of opposite signs via eigenvalues of given matrix. And in this case, it is the distance to instability. Here is an example. Given orthogonal matrix, its eigenvalues, matrix P, the distance equation, the distance to instability that we have found, and the destabilizing perturbation. So I'd like to sketch for my talk. We consider the problem of finding real radius of stability for a stable real matrix. We considered two cases, the class of symmetric matrices and the class of orthogonal matrices. And in these two cases, we found the real stability radius, expressed it via eigenvalues of given matrices. These results can help to construct the testing samples with trustworthy estimations of the distance to instability value. But the problem in general has not solution for today. That's all. I wanted to say thank you for your attention.
Other questions?
You use the entries of your matrices as the machine floating point numbers. If you use for the computation of entries double precision, then there will be one round of error. But in the case of quadro precision, it is much lower. The error is much less. So maybe one should simply always use the computation in quadro precision when trying to determine the exact stability radius of the matrix or not. Or it is enough in many applications to use only double precision.
We have obtained the results that are explicit formulas for stability radius for two classes of matrices. And we can use arbitrary precision.
How? In the computer algebra system?
Yes. We express the stability radius for symmetric and orthogonal matrices via eigenvalues of matrices.
Eigenvalues are in symbolic form.
Eigenvalues we can compute with any precision. And then these formulas are explicit. And for these two classes of matrices, we can obtain the result with arbitrary precision.
Thank you very much.
But for the other classes of matrices, the problem has no solution.
Okay. Thank you. Other questions from serious hall and maybe from internet auditory? If not, I think that we should thank Elizaveta again.